In the last video, we were working with an explicit lock or reentrant lock, and I showed you that you can still produce deadlocks with these types of locks. For the explicit lock, we don't have the way to notify all methods to help us out of this ugly situation. But we do have something else, something that gives us more control before we even acquire the lock and jump into a deadlock. I've got my project open, the Consumer Producer project. You remember I included a lock and an unlock call in my read method, removing the synchronized keyword from its declaration. I also removed the read and notify all method calls because these can't be used outside of a synchronized method or statement. Running my code though simply produced a deadlock, so you might have been left wondering, what's the advantage of using an explicit lock here? Instead of the lock method though, I have other methods available, and one of these is the try lock method. This method returns a boolean, so I'm going to wrap this in an if and else statement. This method will test if another thread has already got this lock. If another thread doesn't, then this method will acquire the lock and returns true back. If another thread does have the lock, then this method returns false. If I can't acquire the lock, I need to figure out something else to do. In this case, I'll print that read was blocked. And I'll set as message to false here as well. Now, it's possible by setting the hasMessage flag to false without first reading the message, there's a chance this code will miss a message. But that might be more desirable than blocking here. This method, the try lock method, lets you figure out if there's a better approach than having threads block at that point. Now that I've got my read method using an explicit lock, it doesn't really make sense for the write method to still be using an intrinsic lock at this point. I'll take a minute to implement it with a lock, much like I did with the read method. First thing I'll do is remove the synchronized keyword. Next, I'll add the try block. After that, I'll include the finally block, which ensures that I'll always release the lock. So I'll call unlock in this block. And now I'll start with an if block. Just like the read method, I'll try to acquire the lock before proceeding. Before I add the else statement, I'll remove the notify all call. Inside the else, meaning if the lock can't be acquired, I'll just print a message that this thread, the write process, is blocked, and then I'll set hasMessage to true. Again, there's a chance that by doing this, my code might skip over a write method. It's possible that maybe in the write message, it's more critical to write the message reliably, but you can see this method lets me decide how to code this. I'll just code it this way to make sure my code won't deadlock. Finally, I'll replace the wait method call with thread.sleep500, so this method will only poll the status flag every half second instead of as many times as it can. Okay, so let's run this. You can see that although sometimes our producer and consumer code couldn't get a lock, it still manages to come out okay. This may not always be true, depending on the timing of the reads and the writes, but the code doesn't lock the application up. Still, this might not be an acceptable solution if messages do eventually get skipped. Another option is to use the overloaded version of the try lock method. This takes a number and a time unit value as arguments. I'll do this for the write method. I'll pass 3 and timeUnit.seconds to this method. Okay, so this means this code will wait here up until 3 seconds have passed, attempting to acquire the lock from the consumer code. Unlike the try lock method that has no arguments, this one throws a checked exception, so I'll wrap it in a try catch. I'll catch the interrupted exception, and I'll throw it as a runtime exception instead. That will wrap all this code in another try block, so this code isn't pretty. It's a bit more work and requires more design processes to figure out how to handle these situations. So why does this throw an interrupted exception anyway? Well, unlike the simpler try lock method, it's possible to interrupt this thread before it times out. This might be something you'd want to do if you've identified some problem and really don't want this thread to keep trying at this point. If I run this code, you might notice there's a bit of a wait before my first or second message because the reader got the lock before the writer. the writer is going to wait up to 3 seconds to attempt to acquire that lock. In addition to these methods, the reentrant lock can offer invaluable information about the lock. To show you this, first I'll go to the main method and pass thread names to both of my thread constructors. The names will be reader and writer. Now, I'll go back to the read message on the message repository. In that final else clause, in the println statement where I'm printing red blocked, I'll include the lock itself. I'll do the same thing in the write method. I'll run this now. Now, in addition to knowing the lock has already been acquired, you can see exactly which thread actually does have the lock, which of course is just the opposite thread in this case. You can imagine this would be useful information if you were managing many threads, for example. I'll pull up the documentation for this lock class to reentrant lock to the method summary. You can see there are quite a few more methods than the 6 methods declared on the lock interface. Many of these other methods let us get information about the lock and its owner. You can see a series of get methods here, getHoldCount, getOwner. Though it's protected, we saw the result of that in the toString method. There's getQueuedThreads, getQueueLength, and a couple that take condition as an argument. I'm not going to cover too many of these methods in this lecture. As we progress through the rest of this section, I'll have the opportunity to cover some of them then. This should give some idea that these explicit locks offer information about the state of the lock that you can't get easily from the monitor lock. I do, however, want to talk to you about the hold count. The hold count of a lock counts the number of times that a single thread, the owner of the lock, has acquired the lock. Maybe that doesn't seem to make sense because you might imagine this is always 1. But remember, in this case, the lock is reentrant. When a thread acquires a lock for the first time, the lock's hold count is set to 1. If a lock is reentrant and a thread, in a subsequent method call for example, reacquires the same lock, the lock's hold count will get incremented. When a thread releases a lock, the lock's hold count is decremented. A lock is only released when its hold count becomes 0. Because of this, it's really important to include a call to the unlock method in a finally clause of any code that will acquire a lock, even if it's reentrant. With explicit locks, you're able to have explicit control over when to acquire and release locks, making it easier to avoid deadlocks and manage other concurrency challenges. Locks provide mechanisms for timeouts which allow you to attempt to acquire a lock without blocking indefinitely. Along with timeouts, you can also have interruptible locking which lets you handle interruptions during acquisition more gracefully. You've also seen from some of the methods on the reentrant lock, there's improved debugging methods that let you query the number of waiting threads and check if a thread holds a lock. In addition to these advantages, there are other more complex locking topics such as condition variables and custom lock implementations. While the explicit lock offers all of these advantages, you want to use it judiciously. In many cases, the monitor lock is sufficient and easier to use for basic synchronization needs. However, when dealing with more complex concurrency scenarios, you may need fine-grained control, and explicit locks can be another tool to ensure thread safety. In addition to locks, the java.util.concurrent package offers us concurrent collections and classes for managing a group of concurrent threads. In the next video, I want to start talking about those classes for managing threads. These implement an interface appropriately called the executor. I'll see you in that next video.